Today's we can discuss about short channel effects. We know that to improve the MOSFET performance, we are reducing the channel length. We are scaled down the channel length. So if we scale down the channel length, MOSFET performance will increase. MOSFET speed of operation will increase, but at the same time, it will introduce some non-ideal characteristics, and that effect is called as short channel effects or secondary order effects. So in the secondary order effect, due to this channel, we are reducing the channel length comparable to the depletion layer width of the source and drain junction. So it will induce some non-ideal characteristics to this MOSFET, and that non-ideal characteristics is called short channel effects or secondary order effects. So we can see in detail what is a short channel, what is short channel effects, and what are the different short channel effects. So short channel effect occur in MOSFET in which the channel length is comparable to the depletion layer width of the source and drain junction. So we have scaled down the channel length in order to obtain maximum performance for this MOSFET. So a MOSFET device is considered to be short channel device when the channel length is the same order of magnitude as the depletion layer width of the source and drain junction. So such scaled down MOSFET channel is called as short channel, and that is effective channel length L effective is approximately equal to the source and drain junction depth. So that is, we are reducing the channel length to approximately equal to the source and drain junction depth. So as the channel length L is reduced to increase both the operation speed and the number of components per chip, the so-called short channel effect occurs. So the short channel effect are attributed to two physical phenomena. One is the limitation imposed on electron drift characteristics in the channel, and one is the modification of the threshold voltage due to shortening channel length. So this short channel effect will be contribute to things. One is the limitation imposed on electron drift characteristic in the channel. So that will impose electron limitation on electron drift chara, as well as that will modify the threshold voltage due to the shortening of this channel length, that will modify the threshold voltage. So we can see what are the different short channel effects nowadays happen in MOSFET. So this occur due to the charge sharing between the source and drain and gate. So a triangle region forms both ends, hence the rectangular area under the gate becomes trapezoid. So due to this short channel effect, we can say that charge sharing, so this modifications of the threshold voltage or the limitations on drift motion will happen due to the charge sharing between source and drain and gate. So instead of the rectangular area under the gate, that becomes trapezoid. So we can see that. So this is our channel. So here instead of rectangular region, we have trapezoid near this depletion region. So here also we can see that this when we are shorten the channel, this rectangular area is changed to trapezoidal area. And we have different short channel effects include channel length modulation, drain induced barrier lowering and punch through, velocity saturation, threshold voltage variation, hot carrier effect. We have different short channel effect or secondary effects are there due to the shortening of this MOSFET channel. So the important one is channel length modulation, another one is drain induced barrier lowering, next is velocity saturation, next is threshold voltage variation, and next is hot carrier effect. So this all are known as short channel effects. So we can see one by one here. So first we can see what is channel length modulation. So channel length modulation means as we keep on increasing VDS, the region for which the inversion charge is 0 keeps on increasing for constant value of VGS maintained. Thus, channel length keeps on decreasing. This phenomenon is called channel length modulation. That means if we are increasing VDS, so we can see that we have a MOSFET, there should be VDS, we are applying voltage on VDS and VGS. In that VGS we are maintained as a constant value, then we are increasing the VDS. So if we maintain VGS and if we increase the VDS, the channel inversion charge is 0. That means the channel length near this region becomes 0. That means the pinch of voltage will happen and this pinch off will occur. So that phenomena is called channel length modulation. Even though this channel is length keeps on decreasing, we have the increase in current. So that is called channel length modulation. So for a short channel, if we are increasing the VDS, if we are maintain VGS as constant, so in this pinch off will occur, and after this pinch off, that means pinch off will occur means the channel length will reduce. And even though the channel length is reduced, then also there should be an increase in the current ID. So that's why it is called channel length modulation. So this is similar to base width modulation. Thus we get a VDS term in the expression for ID even when we are operating in the saturation region. So generally the fabrication of the MOSFET device is done in a way such that the change in length given by del L is equal to L minus L dash is low with a change in VDS. So in this figure we can see that original length is marked as L, but due to the pinch off, if you are increase VDS keeping VGS constant, pinch off occur, that means channel length will reduce to L minus L dash. So this channel length now here, that is L minus L dash. So this channel length reduction cause increment in current called channel length modulation. So in this figure we can see that this is showing that this channel length modulation, that means reduction in channel length cause an increment in current. So this region is called L dash, and so this total length is called L. So this reduction is called L minus L dash. So this fabricators will do this fabricator will reduce this channel length modulation by fabricating the device in such a way that the change in length given by del L, that is L minus L dash, is low with a change in VDS. To make this MOSFET device more ideal, for a short channel MOSFET device more ideal, during the fabrication time, to reduce the channel length modulation, we will give the channel in, we will fabricate the MOSFET device in such a way that the change in length, that is del L, is reduced by a factor L minus L dash with respect to the change in VDS. So we can see in graph. So this is our half mu n COS W by L, VGS minus VTH whole square is the saturation current. So we can see that this current, this for a short channel MOSFET, this is the saturation current. In that we have a factor of 1 plus lambda VDS. So if we are reduce the channel, then if we are increasing the VDS keeping VGS as constant, the channel length will reduce. That means pinch off will occur. That means saturation region will come. Even though this for an ideal MOS structure, we studied that for a saturation region the current is constant, but here the current is instead of constant, it will increase. That's why it is called channel length modulation. So the original observation that the current is constant in the saturation is not unique. Saturation region is not quite correct. The end point of the channel actually move towards the source as VD increases, increasing ID. Therefore, the current in the saturation region is a weak function of the drain voltage. So we can see that actually for ideal MOSFET, the current equation at saturation is ID equal to half mu n COH W by L, VGS minus VTH whole square only. But for a short channel, this current, in addition to that factor, we have another factor, that is 1 plus lambda VDS, where lambda is the channel length modulation parameter. So we can see that even we are increasing VDS, for an ideal MOSFET the current should be constant, but for a short channel MOSFET, even if we are increasing VDS, keeping VGS constant, the current ID also increases by proportionally this with proportionally VDS. So that effect is called that effect is called channel length modulation. So we can see that unlike the early voltage in BJT, the channel length modulation factor can be controlled by the circuit designer. So this base early voltage we can't control, but this channel length modulation we can control by the circuit design time. So for long L, the channel length modulation effect is less than that of short L. So this is long channel and this is short channel. So we can see that for long channel the ID increment is less. That means after saturation the ID is almost constant. But for short channel, after saturation the ID will start increasing. The ID is increasing. That's not constant. So that is called channel length modulation. So even though the channel is reduced, then also ID is increasing. That's why it is called channel length modulation. So next secondary effect is drain induced barrier lowering. That's we can see in another video.